All right, today we are diving into one of the absolute cornerstones of data science, linear regression. We're going to go all the way from the big idea behind it to the actual Python code you'd write, so you can see how it all clicks together. Let's get started.
So let me ask you this. Have you ever wondered how we predict things? I mean, how does a website estimate a house's price just from its square footage? Or how can a company predict what a new employee's salary should be based on their experience? It all boils down to finding the relationship between those things. And the answer, as you've probably guessed, is hiding in the data. There's a powerful technique called regression that lets us uncover these patterns. It sounds technical, I know, but it's a huge part of machine learning, and the core idea is actually way more intuitive than you might think. Okay, so here's our game plan. We'll start with what regression even is. Then we'll zoom in on the simplest version, simple linear regression. We'll talk about how to make it more complex and a huge trap to avoid called overfitting. Then the fun part, we'll see it in action with Python. And finally, we'll wrap up with the key takeaways. All right, let's start at the beginning. What is this whole regression thing anyway? At its heart, you can think of regression as a kind of matchmaker. We've got our inputs, things we know, like years of experience. And we've got an output we want to know, like salary. Regression is simply the method for finding the perfect mathematical formula that connects those inputs to that output. So, with that big idea down, let's get specific and talk about the most fundamental type of all, simple linear regression. And yeah, the name kind of gives it away. We're talking about straight lines. But before we can find the best line, we have to ask, how does a computer even know what best means? Well, it all comes down to a simple concept called a residual. And that's just a fancy scientific-sounding word for an error. It's the gap between what your model predicted and what the actual value was. And this visual right here, this explains everything. The green circles, that's our real-world data. The black line is our model's attempt at a prediction. See those dashed gray lines connecting the real data to the line? Those are the residuals, the errors. The entire goal of the algorithm is to find the one single position for that black line where the sum of all those squared errors is as small as it can possibly be. That's it. That's the line of best. Now, a straight line is a fantastic starting point, but let's be honest, the real world is, well, it's messy. It's not always a perfect straight line. So what do we do then? Well, the cool thing is we can build on this exact same idea. What if you have more than one input? Like you want to use both years of experience and level of education? No problem. That's just called multiple regression. And what if the pattern is clearly a curve? Again, no problem. We can use something called polynomial regression to fit a curved line. But here's the thing to remember. The underlying goal is exactly the same. It's still all about minimizing those errors. But, and this is a big but, with this new power to create complex models comes a hidden danger. It is a classic trap in machine learning, and it's called overfitting. It's basically what happens when your model gets a little too smart for its own good. This image just says it all. On the left, we have a model that's way too simple. It's a straight line that totally misses the actual trend in the data. That's called underfitting. Now, look at the right. That line is going crazy, twisting and turning just to perfectly hit every single data point. That is overfitting. Here's the crucial difference. The overfit model hasn't actually learned the pattern. It's just memorized the data, including all the random noise. It's like memorizing the answers to a practice test. Sure, you'll get a perfect score on that test, but as soon as you see new questions, you're toast. An overfit model will fail miserably when you show it new, real-world data it's never seen before. So what we're really looking for is the Goldilocks model, the one that's just right. You can see it here. It smoothly captures the main curve, the real trend, without obsessing over every single little data point. It has successfully separated the signal from the noise, and that is the key to building a model that will actually be useful. Okay, that's enough theory. Let's get our hands dirty and see what this actually looks like in Python. And I promise you, it's way more straightforward than you're probably imagining. Honestly, when you get down to it, it's just a simple 5-step recipe. First, you import your tools. Second, you load up your data. Third, you create the model and tell it to learn from the data. Fourth, you check its performance. And fifth, the best part, you use it to make new predictions. And this is where Python just shines. Thanks to an incredible library called Scikit-Learn, all of that complex math about minimizing residuals, it's all handled for you. The entire process of creating a model and training it comes down to just one single, beautiful line of code. So after we train the model, we have to grade it, right? We use a score called R-squared. You can think of it as a percentage. A score of 0.862 here means our model can successfully explain about 86% of the variation in the data using our input. In most cases, that's a really solid result. And now for the payoff. This is what it was all for. Once the model is trained and you're happy with its grade, you can use the predict method to ask it for predictions on brand new data it has never, ever seen before. This is the ultimate goal of the whole process. Whew, we've covered a ton of ground, I know. So let's just do a quick fire round of the most important things to lock in. First, regression is just about finding relationships in data to make predictions. That's it. Second, simple linear regression does this by finding the one straight line that has the smallest possible errors. Third, be careful with complexity. A model that tries too hard will just end up memorizing noise, which is called overfitting. And finally, amazing tools like Scikit-Learn and Python make all of this incredibly accessible to everyone. So, we've seen how powerful linear regression is for finding these simple patterns in our data. But what happens when the real world is even more complex than a simple line or a curve? What if the thing you want to predict isn't even a number, but a choice, like yes or no? Well, that's the next step on the machine learning journey.